Clojure lets you write concise code. A major factor that supports this fact is its rich standard library. So far we have studied syntax, build tools, and NRepel. In this module, we'll build on top of that knowledge and understand the most commonly used functions. We highly recommend that you follow along and try the examples yourself using inline eval. This is also a good time to practice some paredit commands. We will reuse the setup for first project and create a new namespace for each chapter. So start your watch process, start the node runtime, and connect your editor to the REPL. In this chapter, we will learn about various conditional functions. The code examples are present in the first project.conditionals namespace. What is the correctest path for this namespace? If you guessed it right, great. If you got it wrong, you might want to review the chapter on project structure again. We have seen a function already. It takes 3 arguments, a variable to check, an S expression to execute if the variable is truthy, and 1 if the variable is falsy. Empty data structures like lists, vectors, and maps are truthy, whereas nil is falsy. You might find yourself in a position where you need to execute more than 1 S expressions in the if or else block. For example, instead of just returning the string, what if we wanted to print and return like so? This S expression is invalid and wrapped in a comment so it doesn't interfere with other example. In cases like these, you can use a do block. Do takes an arbitrary number of S expressions and executes them in order. If not is similar to if, except it executes the first block if the variable is falsy. The function is same as wrapping if with a not function. Not enforces the Boolean value of a variable. Some if statements might not care about the else clause. For example, you might want to render a component only when a variable is truthy. The when function can be used in such cases. It takes n arguments. The first argument is the Boolean expression to evaluate, and the rest of the arguments are the expressions to execute. When also has a when not equivalent, which is similar to when, except it executes the block only if the test variable is falsy. In cases where when or when not do not execute, nil is returned. Cond, or short for condition, is similar to switch case. Cond takes even number of arguments, where the arguments in even positions are the expressions to test and the arguments at odd positions are the output of those expressions. It also takes an else block, which acts as a catch-all. If the else is not specified and no case matches, nil is returned by default. If you write this function in your editor and try to execute testx91, you might see an error saying that testx is not defined. This happens if you skipped the evaluation of the definition of testx function. Your options here are to save so that the shadow watch rebuilds the process, or to inline evaluate the definition of the function. Conp is a modified version of cond that takes a predicate function, a value, and a test value. For each case, the predicate function is called on the value and test value. The cond version of test y function would look as follows. Case is similar to conp equal to. In conp and case, the else blocks are not explicit, but the last element is considered to be else by default. In this module, we learned about various conditionals and also gained our knowledge of NRepel and paredit. Just like the chapter on paredit, think of this chapter as a reference. It will not be fair to assume that you would memorize the entire API in one sitting. Try it once and refer to it as many times as you want it. If you ever get stuck and need more examples, you might find clojuredocs.org website to be helpful. All Clojure data structures are immutable. However, the real world might not always be so. Any useful application would have some state that changes over time. Clojure atoms are thread-safe constructs to accommodate a mutable state. In a true multi-threaded environment like the JVM, atoms guarantee atomic updates across threads. The examples in this chapter reside in the first project.atoms namespace. We suggest you create this file and follow along. New atoms can be created using the atom function. This function takes the initial value of the atom as an argument. The initial value can be anything, a number, a map, a function, or even other atoms. The atom function also takes two optional keyword arguments, a validator, which is a predicate function that's run each time before updating the value. If this returns false, the value is not updated. And a metadata map, which is a set of key-value pairs to hold Atom's metadata. If you eval an Atom N9, you'd see its initial value and the wrapping object. This might differ depending on the language underneath. For JavaScript, it looks like so. A Clojure Atom is an instance of a Clojure ref, or reference for short. We will not go into the details of refs right now, but you can think of a ref as a base class for an atom. To get the current value of an atom or any ref, we need to use the deref method. There are two ways to dereference: the literal way using the @ prefix and the functional way using the deref function. If you want to update the value without caring about the initial value, you can use the reset function on an atom. This function takes two arguments, the atom to reset and its new value. The functions ending with an exclamation sign conventionally denote an unsafe or impure operation. The exclamation sign is usually read as bang. If the new value was set on the atom, then the newly set value is returned and the atom is updated in place. If the value is not set, maybe because it failed the validation, an error is raised and the atom is left untouched. In cases where the update depends on the previous state of the atom, for example adding to a vector, the swap function can be used. Swap's signature is swap, atom, f and args. And args signify 0 or more additional arguments. F is a pure function that is called with the current value of the atom and the arguments passed along. The atom's value is then updated to the return value of this function, and a newly set value is returned. Conj and pop add an element and remove the last element from the vector respectively. Assoc or associate adds a key value pair to a map. Do you recall your first encounter with these functions in the syntax and native data types chapter? Do you remember the immutable nature of these operations? Assoc does not update the original map but returns a new one. Atoms help us mutate state safely. You can add a hook that watches changes made to an atom state. This is useful in cases where you want an impure operation to run after the state has changed. For example, you might want to log the changes or re-render the UI when the atom updates. The addWatch function takes an atom, an identifier keyword, and a function to be called when the state changes. When the reset function is executed, a log statement is printed in the runtime, i.e. the running node script. A watcher can be removed using the removeWatch function by passing in the atom and the ID of the watch. So far, all the atoms that we use were defined using the def macro. The variables produced using def are global in that namespace. The let function lets you define local variables. A let definition is also called the let binding. Let requires a vector with an even number of elements. The variables defined in a let binding are available only inside the let closure. The last element of the let list is the return value. In this example, the atom A will be returned on evaluation. The usage of let binding is not limited to atoms. Any valid closure data structure can be defined in a let binding. In this chapter, we learned about atoms and how to handle mutable state. We also learned that atoms are implementation of Clojure refs. We saw how to watch changes and execute side effects on atoms, and closed with the introduction to let bindings.